In the last video, we saw how to describe the arc length for a curve that was parameterized by one parameter, but in 2 dimensions. So now suppose we have a curve in 3D, and which is parameterized by, let's say, x is f of t, y is g of t, and z is h of t. And so that traces out some curve in space as t ranges over some set of values. Let's say t goes between a and b. Okay, so this gives us a curve in 3 space. So some curve running around like this, somewhere in 3 space. Okay. Um, okay, and so now we're going to ask, what is the length of the curve curve traced by this parameterization as t goes from A to B. So the parameterization, let's say t equals A starts at this point, and then the curve gets traced out as t moves along until you get to the point on the curve where t equals B. Okay, and so at that point, at t equals A, the coordinates of the curve are f of A, g of A, h of A, and similarly, f of B, t of B. I'm sorry, f of B, g of B, t of B. My goodness. F of B, g of B, h of B at this endpoint. Okay, and we want to know if you wanted to lay a piece of string along this curve, how long would that string have to be to fit it exactly? And so it's not hard to see. It's a little hard to draw, but it's not hard to see from the 2-dimensional formula what you expect and what in fact turns out to be correct for the 3-dimensional arc length. It will be the integral from A to B of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared, square rooted dt. So it's a little hard for me to draw the appropriate, no, it's darn near impossible for me to draw the analogous pictures in 3 dimensions as the Khan Academy did so well in 2 dimensions. But it's easy to believe that this is correct. And I know that's not a proof, but we're going to just take his word for it since my artwork is very lacking. And you can't find good videos of this on the web where you do see nice uh, artwork. Okay, so let's think about this for a minute. F prime could be just as well represented by dx dt because f at t is x. So I can rewrite this equivalently. L is the integral from a to b of the square root of dx dt dt squared plus dy dt squared plus dz dt squared square rooted dt. Okay, now if you think about that for a second, that is exactly the length. If I think of r of t as the vector that traces out the endpoints of this curve with components x, y, z, which is f, g, h. Okay, and so x, y, and z depend on t through the parameterization. And so this integrand, or equivalently this integrand, is exactly the length of the vector r of t squared, the length of the vector r of t. Because how do you take the length of a vector? You take each of its components, you square it, add them up, and then take the square root. So another way to write the arc length, a third way to represent it, is it's the integral from a to b of the length of r prime of t dt. Okay, so that's the length of r prime of t. It's important. Let me put that a red highlight there. It's the length of r prime of t dt. Okay. All right. So we have equivalent formulas for arc length. This, or this. The last one turns out to be pretty darn convenient to remember, and we'll see it come up in other contexts as we move along in this semester. Now, sometimes it's very useful to define the arc length function. My pen is strong and bleeds through the paper sometimes. So we define the arc length function S of t by S of t, and it's traditional to use little s, nearly everyone does, is the integral from a to t of the length of r prime of u du. So here you think of u as a dummy variable because t is the upper endpoint of the integral. So we can't use t as the dummy variable inside that integral. Okay, so let's say equivalently, we could write that as the integral from a to t of the square root of dx dt squared plus dy dt squared plus dz dt squared square rooted dt. Well, I should say du because we're thinking of these as functions of u. Okay. And what does s of t represent? So in this way, s of t represents the length of the part of the curve between r of a and r of t. Okay. Okay. So now, if you look at this formula, so let's make a note of that. This is going to come up several different places in the semester. So here's how we define the arc length function, and this is the main formula I want you to remember for that. Okay. Now, the fundamental theorem of calculus, really important in a course called calculus. The fundamental theorem of calculus says if this is the function s of t, and it's defined as the integral from a to t of some function integrated with respect to a dummy variable, then the fundamental theorem of calculus tells us that the derivative of s prime, the derivative s prime of t, is the integrand evaluated at the upper endpoint. So that direct application of the fundamental theorem of calculus from calculus 1 says that s prime of t is the length of r prime of t, period. Okay. Okay. Now we need to remember this. This is going to come up in a bunch of different places throughout the semester. So the derivative of the arc length function is the length of the tangent vector to the curve. It's another way to say that. Okay. Now, sometimes it's more convenient to parameterize the curve in terms of arc length rather than in terms of the parameterization variable. Um, so let's look at an example of that. So sometimes, for example, you might want to say, I give you a curve R of t, which is cosine ti plus sine tj plus tk. Okay. And if you remember, we've seen this curve before. That curve, when you plot it in space, is a helix, and it goes up as t goes up. So suppose I want to parameterize this helix in terms of arc length. And we're going to go from the point 1, 0, 0 in the direction of increasing t. Okay. All right. So the first thing we want to think about is 1, 0, 0 corresponds to what value of the parameter? Well, when you're at 1, 0, 0, that says t equals 0 because the last point is the z coordinate that tells you t equals 0. And then look, that works. Sine of 0 is 0, so we're good. And then cosine of 0 is 1, so we're good. So this corresponds to t equals 0. Okay. And now s, the arc length function, I should say s of t, is going to be the integral from 0 to t of the length of r prime of u du. Okay. So what is the length of r prime if I call the variable u? So what if this is my function r, then what's the derivative? Well, it'll be minus sine t times I, cosine t times j, plus k, right? Let's write that down. R prime of t is minus sine t I plus cosine tj plus k. Okay. So now I want to compute the length of that vector. So this will be the integral from 0 to t of the square root of sine squared t plus cosine squared t plus 1. That's 1, and 1 is 2. Whoops, and I had to do du. Sorry about that. So this is the integral from 0 to t of the square root of 2 du, which will give me the square root of 2 times t. Okay. So the variable s is the square root of 2 times t, which is equivalent to saying that t is s divided by the square root of 2. Okay, so if I want to reparameterize my helix in terms of the arc length variable instead of in terms of t, then r of s is exactly cosine of s over the square root of 2i plus sine of s over the square root of 2j plus s over the square root of 2 times k. Okay. And Why is that convenient? Well, it tells you how far you are along the position vector by how far along the curve you've moved as you went from the initial point to this point, to the whatever point you determine as on the curve. Okay. Um, Now, another thing we're going to want to talk about, or another definition we're going to need in the next little section, is to talk about a smooth parameterization. We say a parameterization is smooth on an interval. Sorry, we have to say on an interval where it's smooth. Interval I, if R of t is continuous on I, and R prime of t does not vanish on I. So the derivative doesn't vanish on I. Okay, so if you think of R as describing a position, then this says the velocity can never be zero when the parameterization is smooth. Okay, and so this is definition 1 and 2. We say a curve C is smooth. The curve is smooth if it has a smooth parameterization. That is, there exists a parameterization so that the parameterization is continuous as a function of t and the derivative never vanishes. Okay. Okay. In our next, so essentially what that means is that the curve has no corners or cusps. And so as it turns, as the curve makes turns, it does so nice without any sharp peaks. So you don't have pieces of the curve going along and doing anything like that. That's a no-no on a smooth curve. Okay, that's a cusp. Um, okay, so in the next section, we'll begin to learn how what we mean by curvature and see how curvature relates to the arc length function that we mentioned before, and we're going to want to look at our unit tangent vectors. We're going to want to think of the tangent vector as being parameterized in terms of arc length. Okay, that's it for this one.